let's get started on chapter 16, which is on vector fields, or the whole chapter is what's called vector calculus or vector analysis, at least the beginning concepts of that. So, an idea, first of all, of a vector field, simple one to know or think about is like wind and particles moving or flowing. So you have these vectors that look like this, and it might start changing directions a little bit. So at each point, there's a speed and a velocity. So maybe in and around mountains, you're going to see a really higher velocity, and then as it comes out, a slower velocity. And it'll be indicated by the arrows. Other fields, vector fields, gravity, electrical fields, magnetism. Those are what you would think of as vector fields. So this is the basic form we define a vector field with, usually capital F or G of X, Y, Z, and then MI, NJ, and then P times K, where M, N, and P are functions of X, Y, Z. So your input is in 3D, right? So some point in space, and your output is a vector in space, right? That's a vector function. So we'll just get started quickly here by sketching a vector field. So suppose f of x, y. This is just the 2D case. So f of x, y is x plus y, 3y minus x. So you can write it in that component form or with the ij form. And this is just plotting points. So I'm just picking some points to plot. Okay, so check this out. Okay, and you get the vectors. You get this vector, and this vector. So that's just a couple examples of what you're getting. So you're getting vectors once you plot points. Okay, so then now we want to talk. So that's the concept of a vector field. Now we want to talk about a couple different things. One's a line integral. So suppose a curve C is defined by r of t. So it's x of ti, y of tj, z of tk. So that's a curve in 3 space. It's smooth, meaning that the partials exist and are continuous on some interval and not simultaneously zero. Okay. A curve is piecewise smooth, basically if it's smooth on a finite number of subintervals. So the one I drew here, this has what, 1, 2, 3 subintervals from A to B. So that's piecewise smooth. Okay. So we define C with R of T, as mentioned, and a line integral basically is integrating over the line, but you're multiplying by some function, which could be like a density function. So you could talk about the density of a wire, or not density, mass of a wire, if the density changed. So if you take out this, the f of x, y, then you just get length of the curve. And I zoom in a little bit on this. This is we call those delta s's, here and here and here and here, that you're adding up. So you're adding up those little pieces. So that's basically the distance formula, and we derived that earlier. You'll see a familiar ds. So your ds is the magnitude of r prime dt. We derived that a bit ago. Before or after spring break, I don't know, probably before. So the square root of the sum of the squares of the derivatives of the components. And I mentioned earlier, yeah, so if f of x, y, z is 1, then you get length of the curve. But think of it, the easiest one to remember about those is I think density. So if you have a varying density and you're adding up length, you have basically a density function that's determined by the curve, a point on the curves. Okay, so it's these evaluation formulas that are really the most important to remember. And I have them highlighted, I think, throughout here of which ones to use. Because you'll see anytime you have the ds in here, you can't really do anything with it. You need dt to do the evaluation. All right, so this is the one you're going to use for the evaluation formula, this one or this one. And here's an example. So evaluate the line integral 2x squared y ds. And of course the ds, we got to change that. We don't know what ds means. So, excuse me, define the curve parametrically. X is t, y is t squared, t negative 1 to 2. Okay, so then f of x, y can be written as 2t to the fourth. So once you substitute for those, we get that. And then you can calculate ds. Okay, so ds is going to be, so here's your ds. And so each of the derivatives are for x. So x would be just 1. That'll be 2t. And then you square it. 1 squared, 2t squared, square root dt. So this is your ds right here. So that's the integral. This one works out nice. Well, I don't really remember actually. This isn't all that nice. Because you have t to the fourth and a 2t. So that would take some work, I think, to look at. All right, so check it out, see what you can come up with. I wouldn't spend a whole lot of time on that. The setup really in this chapter, these chapters are the most important. And here's what I mentioned about mass of a wire. All right, moving on. 16.2 is on line integrals and vector fields. So now you're combining the concept of the vector field I talked about and a line integral. So suppose you have a curve C like this, and it's defined by R of t. So you have some sort of R of t defining that. Then you have R prime is this tangent vector. You can normalize it or unitize it, make it a unit vector. And then you have a force field going through it. So the force field goes like this, and you could picture it as like acting on whatever makes up that C. So if C is like a particle and F is a like magnetic field, then it's going to act on that particle somehow. And okay, so if it's maybe pushing it, or maybe this is wind, and this is some sort of particle moving, then work is defined by force times distance. So we covered this way back. So F dot T is the calculation for work. So it's the projection of F onto the unit tangent vector, which is that. So F dot T is the projection of the force vector onto the unit tangent vector. All right, so work is defined to be the sum of all of those projections. Everywhere you go, it's the projection on that. So again, this formula, not so easy to work with. So here's a little derivation of how to get that. F dot T ds. Here is T, ds is this. These reduce, and so this is the evaluation formula you want to use. Let F be a smooth curve, let F be a continuous vector field defined on a smooth curve C given by R of t. And so that's the hypothesis. So it has to be smooth curve, and F is a continuous vector field. So those components M, N, and P, those functions are all continuous. That's what they mean. So work is that of the vector field acting on whatever, on the curve, essentially, is the sum from A to B of f dot r prime dt. So the r prime dt is kind of like in the direction of, it makes everything go in the direction of the vector field, and to the unit tangent vector, lines them up. Okay, so that's your calculation formula, the one I highlighted there. So let's take a look at this example. Let f of xy be yzx, be a force field. Find the work done by f of xyz along the twisted cube. Now, you don't have to actually know what the twisted cube looks like. You could graph it parametrically. You could get a graphing utility or something. Check that out. You don't really have to know. All right, so we'll define r of t by parametrically, right? So here's your x, y, z, x, y, z. And then you're going to need r prime. So you calculate r prime. And then f of x, y, z. So this was given, right? That's just above. I'm just writing it out in this form is all. So now it's in terms of t. Capital F is in terms of t, the force field. So you can do the dot. So f dot r is this. And then you're just going to integrate. Once you have that, it's pretty easy. You just integrate with respect to t. Those are all polynomials in this case, and you get your value. Okay, next. First, I want to define the gradient of f. And I don't see any other description on my notes here. Okay, so del f means this. It's basically like an operator, or the del is like an operator. So if you say del, that's like, think of that as like a partial x, partial y, partial z, and it operates like multiplication. Like just multiplication by itself doesn't really mean anything. You got to attach it to something. So same kind of idea. You can think of that like a dot product. Oops, didn't mean to do that. Like a dot product, and that's a vector. So definition of a conservative vector field means this. So this is an important one that I might ask. Now I'm going to be very specific. All right, so a vector field F is conservative if there exists a little f such that F is differentiable and capital F is equal to the gradient of F. F is called, if you can find that, right? And so you're going from a higher level function, if it's like a polynomial, to a lower level function once you do its gradient. But look what type of function it is, right? We're saying those are equal. So if they're equal, this is a vector valued function. F was originally, little f, a real valued function. So if you can find that little f, that's called the potential function, and then f is what we call conservative, which has a lot of implications. So here's a simple case that you can just kind of look at. If capital F is 2x and 4y, then can you think of a little f, a real valued function whose gradient would equal that? Well, what if you had x squared and 2y squared? Then take this partial and you get 2x. Take this partial and you get 4y. Right, so those partials give you what you need. So then the gradient of f has to be this, the 2x plus 4y, not plus, 2xi plus 4y. So if you can find a potential function like that, f is conservative. That's the definition. Now, conservative vector field has implications we'll talk about a bit later. So now let's talk about, how do you know whether you can find that potential function or not? That has to do with this test for conservative vector fields. Now, this is the 2D case. So let's take a look at this. Let M and N have continuous first partials on an open region R, okay? Capital F of xy is equal to Mn is conservative if and only if partial n with respect to x is equal to partial m with respect to y. So it's nx, my. If you can say that those are equal, then it's conservative. So check the one above on your own and make sure that one works. Okay, and so that one works above. And we're going to be using this a bit later. I'll show you some more examples. All right. I think this is a couple of things I left out. Okay, so differential form looks like this. So this is the form where we just talked about. The differential form looks like that. So work is integral of each one of those individually, the m, n, and p, and then dx, dy, dz. Okay, so this is the differential form. Sometimes we use that. Wouldn't worry about it too much unless it comes up at this point. Okay, so this is in differential form, and let's just do the calculation. All right, so try this one. So evaluate this along C given by cosine t sine t. So if x and y are given like that, you got to do the partials or the derivatives with respect to t and on each case. So integral of 2xy dx, 0 to pi over 2. All right, so then here's 2xy, 2xy. And then here is your chain rule. And then x squared, y squared. I think I did that separately. Yeah, so I did that separately. Okay, so I'm doing one at a time. All right, so I'm going to erase this later, but I'm doing this one first. And then I'm doing the other one. Okay, so I'll get rid of that. And then I'm going to do this one. Okay, so they're separate integrals, and then let's add them together. So when you substitute in for x squared plus y squared for x and y, then that's Pythagorean theorem. You just get 1. So that's just 1. Then you got to do your dy. So your dy is cosine t dt. So here's your cosine t dt. Then you integrate. Here's your sine, etc. And you get 1. So you just add up this plus this, gives you 1/3. Okay, so next definition is concept or definition of curl. So let f of x, y, z be m, n, and p. Okay, so there's your vector field. Then the curl of f is defined to be the del cross f, del cross f. So the gradient cross f, you can do this determinant, and then in here you put in the operator, you put in the partials, and then you take that determinant. So you cross out these and do this. So partial yp minus partial nz, right? So you go down the line. All right, so if you were to eliminate this, and you just look at this difference right here, actually, no, it's this one. This difference has to do with single variable stuff, or not single variable, but 2D. All right, so this is used for a couple things. It's used in some theorems we're going to do. It's also used in testing for conservative vector fields. So here's a theorem for test for conservative vector field in 3D. If f is conservative, if and only if the curl of f is equal to 0. So if the curl is 0, f is conservative. And curl has to do with, like you could think of it as like swirling motions. So at each point, so it's hard to draw that. So at each point, is there any kind of like swirl? Like if you think of like a circle or a disc rotating, there's no other eddies going on in there. There's circles. But if you think of like a whirlpool, the middle part's going really fast, but the outer part's going slower. Then that would have a non-zero curl. Look that up. That's one of those good ones to look up. I'm sure they have some good animations for that. All right, so here's an example just to determine if f is conservative. So here's your f, and you do the curl on it, do your calculation, and this is not 0. So if it's not equal to 0, it's not conservative because it's an if and only if statement. Okay, next definition is definition of divergence. So let f of x, y, z be m, n, and p. The divergence you can see is del dot f. So if you do the dot product, what type of function does this end up being? So that ends up being a real valued function. So this is real. So that's real valued. Okay, so that means you're going from basically a vector field. By doing this operation, you get a real valued function. Okay, so we'll do this isn't an example for divergence. We'll do that later. The next example you can try is oh no, this one you got to work out. This one takes some time. Okay, so show that it's conservative. So first you do the curl. So the curl of f. So here's your f. You do the curl. Let's do this on your own. Take some time. Okay, and you should get 0. Therefore, f is conservative. And if you know it's conservative, then there exists an f such that gradient of f is f. So that means there exists a potential function. Okay, so that's the potential function. So this is more like how I'll have you do something. So find the potential function. This technique's important for other stuff you do. So potential function, basically you have this setup. Okay, so you say that, so where's my initial one? Here's my capital F. So that means each one of these functions individually was or is a partial of f, little f. So partial fx has to be this, partial fy has to be this, partial fz has to be this. So then what you do is you integrate each one of those separately. So f of x, y, z, so that's what we're looking for, is going to be the integral dx, partial fx dx, and you substitute that in. So so you evaluate that, and then it's going to be plus, not just a constant, not just a, it's a constant that's, or I'm sorry, it's a function of y or z or a constant. So if you were to go the other direction, this way, and do a partial with respect to x, then this would be gone, right? So you'd end up with just the y squared cosine y. So you do that for each function. So here's your integral fy dy. You integrate this, and you get this, and then it's going to be plus some function of xz. Again, if you went backwards and just took the partial with respect to y, then this would be gone. So you do the same technique for z, okay? And so then you just compare them. There's other ways of doing this. This is, I find, the easiest way to do it. You do that, now just compare, which don't repeat functions. So you have this function repeated here. You have this function repeated here. And there's no more. So here's your y, or here's your x, here's your y, and here's your z. All right, so partial x, y, z, which is this, has to be a combination of this one and this one, plus a constant. So here's your y squared zy plus ye to the 2z. And now it is actually plus an arbitrary constant. Okay, so you calculate each one of those, x, y, z, or the whole thing, right? X, y, and then z. Set it up like this. And then don't duplicate your functions that are there and write down each one. And then plus your constant. So that's what your potential function is. Okay, so we're going to talk about next, independent of path. This is an important concept. Has to do with conservative functions. So independent of path basically means, so you have some region, R. Okay, it could be the entire plane, it's okay. And this idea you have some sort of vector field. So F is your vector field going through here like this. So here's your F. You're acting on the particle or whatever. And then if you go from A to B, that path, or A to B, this path, the path being C1 or C2. If you could do any path you want and get exactly the same value for any path, then that's what we say is independent of path. That's the idea. So if C1 and C2 are arbitrary, meaning any two different paths, and the integrals are equal, then it's independent of path. So if you subtract them, you get 0. So in other words, if you go this way and then you come back and you get 0, for any path you take, then it's conservative. And we call it independent of path. Okay, so to get in more to that, we want to talk about a couple definitions for regions. A region R in 2D or 3D is called connected if any 2 points in R can be joined by a piecewise smooth curve lying entirely within R. So this one, we would call it connected because you take any 2 points and you can connect it with a line. Okay, these are obviously not connected because you take there exist 2 points that you can't get from here to the other region without going outside, which is everything outside the boundaries, the region. Okay, so it has to be connected, and that's part of the hypothesis. All right, so independent of path, let R be an open connected region. Let C1 and C2 be piecewise smooth curves lying entirely within R. So it's the one we did above, and it's open. So it does not include its boundary points. So the line integral, f dot dr, is independent of path if these are equal. It's just basically what I was stating. So C1 and C2 are any paths in there. So here's one path, here's another path, etc. Okay, so that's the concept. So if the line integral is independent of path, then f is conservative, and vice versa. So if f is conservative, then the line integral is going to be independent of path. It's like a potential. Think of it as kind of like potential function. Well, not potential function. Like I can't think of the term right now. Like gravity. And it doesn't matter whether you go diagonal to the point or it's conservation of energy concept. So I can't really show you this, but if you go from upper right to lower left or just straight down to the same point, there's no energy loss. It's kind of that idea. So it doesn't matter how you get from one to the other. Next theorem has to do with a closed path. That's this circle means right here. That means a closed curve. So work done on a closed curve, if f dot d is 0, that means f is conservative. Okay, and that means closed curve. Okay, continuing, let f have continuous first partials in an open connected region R. Let C be a piecewise smooth curve in R. And then the following are all equivalent. Okay, f is conservative, there exists a potential function. The line integral, f dot dr, is independent of path. The closed curve, so every closed curve in the region is equal to 0. Okay, and you have to understand that it has to work for every curve. So the fundamental theorem of line integrals states this: let C be defined as above. Okay, so C is all of that. Piecewise smooth curve in R. Okay, and R is a smooth. Open connected region R. Okay, that's what it is. So just defined as above. R of t is x of t, y of t, z of t. F is conservative. Then f dot dr is just basically calculating the potential function at its endpoints. So it doesn't matter how you get from here to here. It's basically all you're doing is calculating this point, and this point. So going like this. You don't have to integrate every little piece and add it up. It's basically whatever is acting on the curve here and here for those individual points A and B. So that's all you end up doing is evaluating at the endpoints. So you got to find potential function or have a potential function, and then subtract. So it's basically the same concept as a definite integral. Right, you're going from a capital F to a lowercase f, so it's just like a definite integral, but these are, I guess, more complicated. Okay. Next, we'll go on to Green's theorem.